Let's discuss 3 problems from today's Division 1/2 round, starting with Division 1A. You can read it now or listen to my explanation. In my words, you are given an array and a sequence of queries. Each query gives you a subsegment. For every given subsegment of the array, you need to tell what is the largest subsequence of this subsegment, which doesn't have 3 non-increasing elements in a row. Let's look at how the resulting subsequence can look like. Suppose we take this element, then that element. The height of the point shows the value of the element. Let's show with blue which other elements the sequence can have, the ones which we did not take into the answer. So obviously there must be no elements in between those two, because even if it's less than this one or larger than this one, we can still take them without losing the correctness of the answer. But it's possible that there is an element here which is larger than the right element of this pair, and that there is an element here which is lower than the left element of this pair. And it's possible that there are several such elements here and there. But this sequence of elements should be not decreasing, because if there is an increasing pair, then we could have taken those 2 elements instead of this one, and the sequence would be larger. And also it's possible that there are some other elements here, but they should be all in between those 2 elements, because otherwise we could have taken them into the answer and the resulting sequence would be larger than the supposed answer. But you can see that we can always transform the answer so that instead of this element we would have taken this element, and instead of this element we would have taken this one. So let's only consider the answers where from a sequence of several non-increasing elements in a row we don't take the middle elements, we can only take the last and the first. So we can only consider the answers in which there are no elements in between an increasing pair of chosen elements, because we can always change the answer to make it satisfy this criteria. So the answers that we now consider will have only such shape. All the elements of the sequence which were not taken to the sequence will be in between a pair of non-increasing elements. We can also say that we can always take the rightmost element of the segment into the sequence, because if there are any other elements in the sequence after the rightmost chosen element, then we can always change this element to be the rightmost. And the same applies to the leftmost element. If there are any elements left out which were less than the leftmost chosen element, then we can increase the sequence. But if they are all larger or equal than the leftmost chosen element, we can either again prolong our sequence by 1 or always change the answer so that the leftmost element is chosen. And with this we have actually shown that we can always just consider one possible answer. It's where we take the leftmost elements of the segment, the rightmost elements, and also every element which is a part of an increasing pair that goes in a row in our original segment. So to quickly calculate the answer for a query, we can simply pre-calculate for every element if it's a part of some increasing pair, then using prefix sums find the number of such elements on this subsegment and just add 2. Except for the case when there is only 1 element on the segment, in that case the answer is 1. Let's look at the implementation. So I read the array, b of I is equal to 1 if and only if the ith element of the array is a part of an increasing pair, otherwise it's 0. So I go through every neighboring pair and I see if it's an increasing pair, then I set b of I and b of I plus 1 to 1. Then I calculate the prefix sums on the array b, and then to answer a query, I first transform it into a semi-interval, then I check if it's size 1, I just output 1, otherwise I take the prefix sum on a semi-interval from L plus 1 to R minus 1 and add 2. Now for the problem B, you can read it now or listen to my explanation. In my boards, we are just given an undirected graph, and we have to find a subgraph of this graph, which is a cycle plus two other vertices attached to the same vertex of this cycle. Or tell that such subgraph does not exist. The constraints are low enough for the square solution to pass, but we will consider a linear solution. First of all, let's come up with the naive criteria when such subgraph exists. Of course, in order for it to be true, there has to be a vertex which lies on some cycle and has a degree of at least 4. If such vertex does not exist, we can safely say that such subgraph does not exist. But suppose such vertex exists. What can go wrong? Well, one or two of these vertices may be a part of a cycle. But suppose first one of them is a part of a cycle. Then there must be at least one vertex here and one vertex here, because there are no multiple edges between the same pair of vertices. But in this case, we can, for example, get rid of this part of a cycle and instead connect the cycle like this and take those two vertices as additional vertices. And the second case is if both additional neighbors of this vertex are a part of a cycle. This is apart from those two neighbors that it already has. In this case, you can take this part with all the vertices that may lie here as a cycle, and those two vertices as additional vertices. Now we basically just need to find a vertex which is a part of a cycle and has a degree of at least 4. In order to find all the vertices which lie on some cycle, I simply find all the bridges in the graph, and for every edge which is not a bridge, I mark the endpoints of this edge as vertices which lie on some cycle, because a bridge is an edge which does not lie on any cycle. So if an edge is not a bridge, then both of those vertices lie on some cycle. Then I try to find a vertex which has a degree of 4 and which is a part of some cycle, and then I simply find a random cycle with it. And then I possibly have to transform this cycle, like in this case or in the previous case. So let's look at the implementation. G will be the adjacency lists. Used is the visited array. Depth and up are the arrays which are needed to find all the bridges. And onCycle is just true if a vertex is a part of some cycle. This DFS function finds all the bridges in the graph. Depth of V is simply the distance from the root of the DFS to this vertex in the DFS tree. And up of V is the minimal depth which can be reached from a subtree of V via a single edge. P is a parent of V in the DFS tree. If this is an edge into a parent, I simply skip it. Otherwise, I see if this vertex is not visited, then I set its depth to be the current depth plus 1, run the DFS, update the up value of V. So if some depth is reachable from the subtree of 2, it's also reachable from the subtree of P. Then I check if the depth which is reachable from the subtree of 2 is not equal to the depth of 2. Then it means there is an escape path from this subtree if I delete the edge from V to 2, which means that this edge from V to 2 is not a bridge. So I mark both V and 2 as vertices which lie on the cycle. And if it's an edge into a vertex which I've already visited, so it's an edge outside of the DFS tree, I simply update up of V with the depth which can be reached through this edge, and I mark both of those vertices as vertices on the cycle, because each edge outside of the DFS tree forms a cycle. And the second DFS function, which I call find cycle, it just simply finds a cycle containing the vertex V. So it's also a DFS, but it returns true if it managed to find an edge into the starting vertex. Here I simply check if 2 is a starting vertex or it is not visited and DFS have managed to find a path from this subtree to the starting vertex. Then I return true, but before it I add V into the cycle, and now I mark it as onCycle. By the moment when I call this function, the on-cycle array is already reinitialized, and now it shows if v lies on the precise cycle we are looking at, not on any cycle. And if we did not manage to find a path, we return false. So here I read the number of iterations, and I start an iteration by clearing all the global arrays, because they were used on previous iteration. Then I read nm, read the graph, initialize the arrays, and I call multiple DFSs. Why do I call multiple DFSs? Because the graph may be unconnected. In each connected component, I find all the bridges and mark vertices which lie on the cycle. Then I'm trying to find the vertex which lies on the cycle and has a degree of at least 4. If I didn't manage to find such vertex, I'll put no. Otherwise, I'll put yes, but now I have to find the right cycle. First of all, I find any cycle using the function findCycle, having reinitialized the used array and the onCycle array. So now onCycle shows if the vertex lies on this precise cycle. Here I calculate the number of neighbors that V has, which are not part of this cycle. If this number is less than 2, then I have to transform my cycle. V lies in the very end of the cycle list. So I want to start deleting the vertices from the beginning of the cycle list until I've deleted at least one and I'm at another vertex which is a neighbor of V. To delete from beginning, I reverse the cycle and then delete from the end. I have to delete at least one forcefully, but then I simply do an endless loop, which will be broken when the last vertex is a neighbor of V. Until that point, I delete the last vertex. And then I reverse the cycle back. But if V has 0 vertices, which are not a part of a cycle, then it means it has to have at least 2 extra neighbors in the cycle. One of them was already deleted from the cycle here, so there has to be another one. And this time I delete from the end of the cycle. I have to delete at least 2, because first one will be V itself and the second one will be its neighbor. And then again I'm deleting the last vertex until I meet another neighbor of V. And when it happened, I push back V back again. Now I want to recalculate the cycle so that it matches the new transformed cycle that we have. And then I output the number of edges, cycle size plus 2. Now V is guaranteed to have at least 2 off-cycle neighbors. So I simply output the edges on the cycle, and then I go through all the neighbors of V, and I see if it's not a part of a cycle, I output the edge into that vertex until I met 2 such vertices. Now for the problem C, you can read it now or listen to my explanation. In my words, we have a polynomial of degree d, modular 10 to the power of 9 plus 7. We are given its values at points 0, 1, etc. d. And also s, s plus 1, etc. s plus d for some s, which is unknown. Our job is to find s. D is large, so the solution is required to be linear. Let's consider a of 0, a of 1, etc., a of d. And let's say that a of x is a0 plus a1x plus a2x squared plus etc. a dx to the power of d. So basically, this sequence is the sum of some arithmetical progression plus some progression which grows at the square speed plus some cubic progression and so on up to the progression which grows with the speed of x to the power of d. An arithmetical progression, or you can call it a linear progression, it will add the same amount every time you move from one element of the sequence to the other. Each time it will add a1 to the value of a. The square progression will first add a2. Then it will add 3a2, because 2 to the second power minus 1 to the second power is 3. Then it will add 5a2, and so on. So the squared progression adds an arithmetical progression to the sequence of differences. And the cubic progression will add a square progression to the sequence of differences, and so on. So if we consider a sequence of differences of the neighboring elements instead of this original sequence, it can be expressed with a polynomial of the power d minus 1. So maybe it's a good idea to consider a sequence of differences between the neighboring elements instead of the original sequence. So I will write out a1 minus a0, a2 minus a1, etc. ad minus a d minus 1. So if I mark this as a prime of 0, this as a prime of 1, and so on, this is a prime of d minus 1, then I know that a prime is a polynomial of degree d minus 1. Let's see what will happen if I apply this operation to a prime. I will write out a prime of 1 minus a prime of 0, a prime of 2 minus a prime of 1, and so on, a prime of d minus 1 minus a prime of d minus 2. If you denote this sequence as a prime prime, a prime prime will be a polynomial of degree d minus 2. So if you keep applying this operation, you will get a polynomial a prime 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 d times. This will be a polynomial of degree 0, so it's just a constant. And we will know its value at point 0 and at point s, because we can do all the same operations to points from s to s plus d. But the value of this polynomial is constant, which means it will be the same for all points. So knowing this at point 0 and at point s will not help us find s, which is our original task. So instead, let's just stop one step earlier, when this polynomial used to be of degree 1. In this case, it can be written down as p plus qx. But when we stopped after d minus 1 steps, we still had two values on our hands. Each time the number of values in our sequence decreased by 1. Originally the size of our sequence was d plus 1. We decreased it by 1 d minus 1 times, so we still have two values, a prime 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 of 0 and a prime 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 of 1. If you substitute 0 for x, you will get that this value will be equal to p, and this value will be equal to p plus q. Now if you apply all the same operations to this sequence, you will get a prime 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 of s and a prime 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 of s plus 1. But it will be just enough to know this value, because we already know p and q from those equalities. And this value, we know that it's just p plus qs. So we can find p as this value, q as this value minus p, and s as this value minus p over q. Q shall not be 0 because this polynomial shall be of degree 1, not degree 0. The only remaining question is how to do this fast. Because if we are to do it the naive way, we will end up in an n-squared solution, or d squared to be precise. So let's look closer at the numbers which we'll have during this process. Let's express those numbers which are the values of a prime prime using our original sequence of values of a. So this is actually a2 minus a1 minus a1 plus a0. So this is actually a2 minus 2 times a1 plus a0. And this can be written down analogously, but instead of values 0, 1, and 2, we will take values 1, 2, 3, and so on. On the next step, the first value of a prime 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 will be this minus that. Let's write it down also using our original values of a. It will be a3 minus 2a2 minus a2. This is already written down. Plus a1 minus 2a1. So plus 2a1. So plus 3a1 in total. And minus 1a0. Okay, we have to find the pattern right now. Look, initially we had 1a0, then we had 1a1 minus 1a0, then we had 1a2 minus 2a1 plus 1a0, then we have 1a3 minus 3a2 plus 3a1 minus 1a0. If you still did not understand it, I will write it down this way. We had 1a0, 1a1 minus 1a0, 1a2 minus 2a1 plus 1a0, 1 minus 3, 3 minus 1. This is a Pascal triangle. Only every second number starting from the right is multiplied by negative 1. And indeed, to find the next line, I should write down this line under that one with a shift of 1 and subtract the previous line from this line. I will get 1 minus 4 plus 6 minus 4 plus 1. So you see, in the Pascal triangle, we would have added up those two lines, but here we subtract them, but it's compensated with the fact that every second number is multiplied by negative 1. So we have verified that the coefficients with which we have to take our original values of a are binomial coefficients. So after d minus 1 steps, it will be just d minus 1 choose 0, d minus 1 choose 1, etc. d minus 1 choose d minus 1. Only every second of them must have a negative sign, starting from right to left. So to quickly calculate the final values of a prime prime d minus 1 times, we simply have to be able to calculate binomial coefficients in O of 1. This is very easy if you pre-calculate all the factorials in before modulo 10 to the power of 9 plus 7 and all the modular inverses for every factorial up to d. Then to find the binomial coefficient, you can just take the pre-calculated factorial times the pre-calculated inverse of factorial times the pre-calculated inverse of some other factorial. Let's look at the implementation. Max d is maximum possible d. This is binary exponentiation. This is modular inverse. This is the array of pre-calculated factorials modular mod. This is the inverted factorials, so they are modular inverses. This is binomial coefficient and choose k. This function simulates the d minus 1 steps of our process and returns the result. We actually have to do it 3 times. First with the values a0, a1, etc. a d minus 1, and the second time with the values a1, a2, etc. ad. And the third time with values as plus 1, etc. as plus d minus 1. So this function accepts a reference to a vertex where those values are stored, and the index of the first value which we want to take. So in the first scenario it will be vector a and position 0, in the second scenario it will be vector a position 1, and in the third scenario it will be vector b position 0. d is just d. So we go from 0 to d minus 1 inclusively, take the binomial coefficient times the original value of a, modulo mod, and if it's needed, we multiply by negative 1 by subtracting current from mod, and then we add it to the result. Here in main, I precalculate all the factorials, and here's the trick how to precalculate every modular inverse of every factorial without having to invert every one of them. You simply invert the last factorial that you need using your function, and then using this formula you can find that actually inverse factorial of I minus 1 is inverse factorial of I times I. Because if you take an inverse of both parts of this equality, you will get inverse factorial of I is equal to inverse factorial of I minus 1 over I. So if you move I to the right, you will get this equality. And this is much quicker because you must remember that our function works in log of mod, because we use binary exponentiation to invert. Then we read D, we read the values A0, etc. AD. We read the values AS, etc. AT plus S. We find P, we find Q, and we find P plus 2S, subtract P, so now R is just 2S. To find S, we just divide it by Q, using the modular inverse. That's it. That's it for today. Thank you for watching, and I remind you that I give private lessons on competitive programming. If you are interested, contact me on Telegram. Goodbye.